Hi, welcome back to Unit 9 for AP Physics C, Electricity and Magnetism. So this is the topic 9.1. So this is electric potential energy. And you can see here just a brief overview that you can see this, again, we're still comparing, making these comparisons between the gravitational pull with this electrical force. And so something you have to remember is discuss the mechanics that any conservative force has a potential energy associated with it. And so electric potential, right, or the electric force is not uncommon to see this potential energy. So something to note that electric potential energy is essentially the amount of work required for an external force to bring point charges to where they are from an infinite distance away. So again, making this comparison to gravitational potential energy. So gravitational potential energy is the amount of work done against gravity and moving an object from one location to another. So it's kind of the same idea. Okay. So the general form of the potential energy equation takes the form of U equals K Q1 Q2 over R. You may also see it written as 1 over 4 pi epsilon naught times Q1 Q2 over R. Again, remember that this 1 over 4 pi epsilon naught, that is K. And we'll dive into in the next slide about where that comes from. But again, in mechanics, you learn that potential energy is essentially the derivative of the force. And so you get the same kind of look for gravitational potential energy when you're off the surface of a planet. And so something that you can see, yes, you're going to have to deal with two charges, but what happens is that it acts differently. So the way you think about it is, opposites attract, likes repel. So what happens is if the charges want to do what they want to do, then you're going to get low potential energy. So for example, right here, here we have an example where you have a positive next to a positive. So they want to separate as far away from each other as they can. So hence the reason why it is a low potential energy. Now, to bring them closer together, you got to do something against what they actually want to do. And that's where you get the high potential energy. All right. So again, if they want to behave like they should, you're going to have low because they want to push each other away from each other. And then if you're going to try to squeeze them together, you're going against what they want to do. So you're going to end up with that high potential energy. Now, on the opposite side, if you have the opposite charges, so it's going to be the opposite, right? And so the negative charge, because it wants to go to the positive charge, you're going to end up with high potential energy. And then you have if you want to bring them apart, right? Because that's what they want to do, right? Or that's what they don't want to do, and you want to pull them apart, they're going to have low potential energy. Sorry, I got that backwards. So if they bring them, if they do what you don't want them to do, okay, then you're going to have low potential energy. And something else to note is that the force always points toward decreasing potential energy. Okay, so if you have positive and positive, negative and negative next to each other, right, that force is going to point away, right, from the decreasing potential energy. Now, the total electric potential energy for the system is just simply finding the sum of the individual energies, okay, or the interactions between the objects. So it follows superposition, right? So you got to take in consideration positives and negatives. If you have a positive and a negative, that ends up being like a negative potential energy. If you have two positives, that is a positive potential energy, okay? And so again, opposite signs, the U is going to decrease, right, when you bring them close together, because that's basically what they want to do. They want to come together. And same signs, the U is going to increase when you bring them close together, because that's what they don't want to do, right? They don't want to come together. All right, so let's take a look at a quick example. So if you want to try this on your own, go ahead and pause the video once I change over to that screen. All right, so here we have a derive an expression question. So derive an expression for the work required to assemble the charges in the configuration shown. So what we're going to do is we're going to take these three charges from an infinite distance and bring them into this equilateral triangle configuration. So remember, work is change in potential energy, which means we're just going to sum up those potential energies, right? And so it's like we have, and we'll call this 1, 2, 3. That'll help because I'm going to write out like K, Q1, Q2, right? So we have K, Q1, Q2 over D plus K, Q1, Q3 over D plus K, Q2, Q3 over D. And now they're all over D, even down here it says D over 2. Well, that distance, D over 2 plus D over 2 is just simply D. All right, so let's plug in what each charge is, and I'm going to factor out a K because K is always a constant. So we're going to do 1 and 2, so it's going to be negative 2Q times 3Q, right, positive 3Q over D, plus, now 1 and 3, so it's going to be the two negatives, so negative 2Q times negative 2Q over D, plus, and then we have another 2, 3, right? Negative 2Q, positive 3Q over D, right? And now we just simplify. Oops, sorry. So I have K times negative 6. Sorry, I don't need the K because I pulled that out. So you have negative 6Q squared over D plus 4Q squared over D plus negative 6Q squared over D. Okay, so I can basically have negative 6 plus 4 minus 6, so it's negative 12 plus 4. That's negative 8. So negative 8KQ squared over D. That is the total potential energy to get these three charges to come together. Okay, so in the next video, we're going to dive more into electric potential. So there's a difference between electric potential energy and electric potential energy, and we're going to dive into that in the next video.